They use an S, which I hate writing up there because I start thinking it's a 5. So I'm just going to use P for position. And some books will have X of T like that for their position. In other words, where is it on the what? X axis. All right? In other words, you know, is it 5 units out here? Then it did it back up to get to 3. And then it turn around and go this way. But anyway, the X. Now, if they do Y of T, they're not talking about horizontal movement. They're talking about what? Vertical. And the reason I'm mentioning that is when you get into two-dimensional, you'll have an X motion and you'll have a Y motion formula. So we're going to start everything we're going to do today is going to be X. And the positive direction for us is to the right. Yes, we could change it. We could, if it made it easier to work the problem, make the positive direction to the left. But let's keep it simple. Let's make the positive direction to the right. Now, let's look at a little bit more terminology. Velocity. Velocity is the change in the position of the particle or the bouncy ball. Particle sounds so physics-like, but bouncy ball. It's the change in the position of the ball with respect to time. If I use the word velocity in here, I am talking about instantaneous velocity. All right? Instantaneous velocity. Average velocity is the position at the ending time minus the position at the beginning time. Ran out of room. Divided by the change in time. T at the end and time at the beginning. End, time, minus beginning time. And that's how you get average velocity. All right? And average velocity can be helpful, and it can be a little bit misleading. But we have a position formula, and velocity is the change in position with respect to time. A positive velocity, you're going in the positive direction. A negative velocity, you're going in the negative direction. So in our case, if I tell you you have a positive velocity, we're going to be going to the right. If I tell you we have a negative velocity, we're going to be going to the left. And then you can learn that information, and then you can figure out how to for something moving up and down. Now, I want you to notice something about the ball as it changes directions. Now, for this case, we're going to make positive going up. So it's going to start off with a positive velocity going up. All right? And that positive velocity going up, and it's going to have a negative velocity coming down. As I throw it up, what happens when the velocities change? What does the ball do right at the moment the velocity changes from positive to negative? It's going up, and then it comes down, but what must it do for just a moment?
Stop moving.
It's got to stop at the top. Right? Yeah. It's going up, it stops, and it comes down. Something very important about all this stuff we're going to talk about is changes in direction. They don't always have to occur there, but changes in direction, look for changes in direction. Doesn't always guarantee it, but for changes in direction, check V of t equals 0. the velocity will probably equal what when it changes directions? 0. Matter of fact, it might. Now, yes, sir.
Hey, I'm sorry.
I notice everybody's 6 feet apart. So if it happened today,
No,
you don't even have to worry about it.
It's not today.
I got the seating chart early.
Seating chart for this class last Wednesday.
Okay, and that's what I turned in, but I even had it.
Okay, I appreciate it.
This is A-Day.
People see me coming in the door, they're like, oh.
He
That's
sat
all right.
there,
He sat.
right there.
Oh, y'all already know who it is.
Yeah.
Oh, yeah.
This is the front of the room right here.
Yeah, okay.
Uh,
We're good, we're good.
Yeah, this class is spread out. Yeah.
I have 3 more classes, or 2 more classes with him, so.
So you know, and you're
When
pulling
I,
up.
when I walk in those classes, if you could just like, you know,
Yeah.
do what you did right there, I appreciate it. Thank y'all.
Now,
4 classes.
seriously, Mr. Bird,
Me too.
starting today, you don't have to check mine. Mine are all 6 feet apart.
I see it.
All right, now we're back to teaching. We're done with the COVID check. So, what we're going to do is we're going to be concerned about when the instantaneous velocity equals 0. Because that's where we're most likely, or that's one of the places to look for what? A change in direction. All right. And honestly, that's the only place you're going to see a change in direction for these problems. There is a way to have a change in direction, but you would have to have an undefined velocity. All right? Well, that's not going to happen. Okay? So students always go, what happens if you had an undefined point? You could have an undefined point and had the velocity go from positive to negative. Yeah, what we're working with here, I haven't taught you because I didn't teach you the limits, but we're talking about a continuous function here. This is a continuous experiment. We didn't have something weird happening in the middle of the experiment. So for us, we're always going to look for change of direction when the velocity equals 0. That does not guarantee there's a change of direction. Mr. Evans starts out with a positive velocity. He gets tired. He takes a break. His velocity is 0. Then he keeps going. Didn't have a change of direction. Right? So just because the velocity equals 0 does not mean there will be a change in direction. Now, let's go ahead and hit the next level. This. The change in velocity with respect to time is called acceleration. All right? Acceleration. And average acceleration, you'd subtract the beginning velocity, ending velocity, and all that. Acceleration, if you take this, acceleration is the change in the position with respect to time with respect to time. Because velocity is what? Change in position with respect to time with respect to time. And that gives you acceleration. And that's instantaneous. Now, if you have a positive velocity, you're going in the positive direction. Acceleration affects whether your velocity is increasing or decreasing, but it doesn't affect the direction except when the particle is stopped. Y'all agree that gravity is a negative acceleration? All right, if you're trying to move up, gravity is a negative acceleration. So you got a positive velocity, but you got a negative acceleration. What's it doing as it goes up? It's slowing down. Once it starts falling, it actually starts speeding up. Does everybody agree it starts speeding up as it falls? Well, in that case, you have a negative velocity and a negative acceleration. All right? Is that okay? All right. And we're going to talk all about that as we go along, but I'm trying to get you some ideas of what the terms mean. Notice I have totally avoided the word speed. Okay. Velocity and speed are not the same thing. They're not. the absolute value of velocity is speed. Speed doesn't tell you the direction. All right? Speed doesn't tell you direction. Velocity tells you the direction. All right? So if I tell you I'm going 75 miles per hour towards Dallas, that's a velocity. I tell you I'm going 30 miles per hour, that's not a velocity. I tell you I'm going 10 feet per second, and if I tell you it's a velocity and it's positive, you got to be going in the what? Positive direction. All right? So speed, if you look at this, it's a negative velocity when it's coming down. But the speed's increasing because it's getting faster as it goes down. The velocity's not getting bigger. Velocity is going to be like negative 20, negative 30, negative 40. Why is that happening? Because it is going what? Down, so I'm calling the velocities what? Negative. And the speed's increasing, so negative 20 miles per hour, negative 30 miles per hour, negative 40 miles per hour. Because remember, speed is the what of velocity. Absolute value. And that's going to cause some problems for us as we go along. Especially since I'm teaching this off the top of my head, first time in quite a while. All right, let's look at how to draw a graph, if you will, or show the motion of this particle on a number line. The line that we're going to draw left to right is not a timeline. It is the number line, it's the position. All right? Think about it. I'm going to count seconds. 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, 6 seconds, 8 seconds, 9 seconds, 10 seconds, 11 seconds, 12 seconds. Those are the times, but my position as I was going left and right is what I'm going to put on my line. In other words, if I made the floor a number line, in the first 3 seconds I went 4 blocks this way. In the next 3 seconds I went backwards 7 blocks. Well, I'd be at 6 seconds here, even though I'm behind where I was at what? 3 seconds. Is that all right? Now, if you're going to work these, and you're going to look at the movement of this particle, the little bouncy ball. Particle just sounds more intellectual. Makes you think you're doing something heavy duty. And this is pretty heavy duty because this gets you started into the world of physics. All right. I'll put my line over here. That's my position, P, and I'm going to put a positive out here so that you know that's the positive direction, right? And it could go back there forever and out there forever. Don't know. Okay, that's my position line. If I put 0 in here, does everybody agree it started at a position of 1 unit to the right? All right, it's 0. I shouldn't say started because you could have negative time. You have negative time in experiments all the time. You watch them launch the space shuttle. That's my time frame. You watch them launch the new satellites for communications, and you'll notice they'll go negative 2 hours, 30 minutes, negative 10 seconds and counting, because the moment they launch is 0. Everything leading up to the launch is what? Negative time. Is that okay? So we're just, when we start our experiment, we're making an arbitrary place 0, and then from that time forward is positive, and if we go backwards from that point, we consider that what? Negative time. Okay? Now, if you were to put 3 in here, that would tell you where the particle was at 3 seconds. Okay? If you put 10 in there, tell you where the particle was at what? 10 seconds. At 0 seconds, it's at 1, and I'm not really worried about that, but I just want to show you it working. Here's what you need to do to map the movement of that particle. Remember the key. It changes directions when the velocity equals 0. That's the only place it can change directions. It may not, but it's the only place it can. So I need a velocity formula. Folks, velocity is the instantaneous rate of change, so take the derivative. Yes, I'm going to use that term, take the derivative. Because what is derivative find? Instantaneous rate of change. That's for those kids that never learn what the word derivative means. They never know why you would take the derivative to get velocity. Because velocity measures the instantaneous rate of change in the position. Now, after you do that, set the velocity equal to 0. When you factor that 3 out, leave it in the front. Because if you don't, you'll make little mistakes later. That 3 might be handy for your velocity formula. Okay? Because we're just rewriting the velocity formula. Right. Keep the 3 out there. Because this is still, if I wanted to put a number in here, I could find out what the velocity is, right? Because this equation is still equal to what? That equation. If you divide 3 out, then you can't just put the number in here and find the velocity. And I want to keep that 3 there just in case I want to find the velocity real easy. Because does everybody agree it'd be a lot easier to put the number in here and work it out than to put it in here? See? So I'll leave that 3 there. We might need it. Okay? Give you a little chance to write and think. Let you write and think. So far, so good? Now, what I'm going to do is I'm going to make a timeline here. All right? Make me a little timeline. Over here, because that's not a timeline over there, is it? Okay, I'm going to make it a little timeline. Timeline. And on this timeline, I'm going to put t equals 1 and t equals 3. Because I do want my times here to go from smaller times to larger times. Now, at that t equals 1, the velocity equals 0. V of 1 equals 0. V of 3 equals 0. What I'm going to do is I want to find out which direction it was moving during this time, which direction it was moving during this time, and which direction it was moving what? During this time. Because I don't have to worry about it changing directions between here and here, because there is no what? Velocity equals 0. Once I find out what direction it's going here, it's never going to change directions. Because in order to change directions, the velocity would have to equal 0. And does the velocity ever equal 0 out there? No. Is that all right? Give me a thumbs up if everyone's following what I'm getting at here. All right. So, what you do, real simply, is you pick a number smaller than time equals 1 and substitute it in your velocity formula. So we'll put 0 in our velocity formula. You put 0 in here, and you find out the velocity is what? Positive. Is that okay? Somebody says, no, I want to test -1. Put -1 in there. You'll find out the velocity is what? Positive. So, for everything less than t equals 1, we have a positive velocity. Which means the particle is moving in the positive direction. For us right now, it's what? To the right. Positive velocity, so our particle is going to be moving that way. Now, our particle is going to run along that way, and at t equals 1, it's going to stop for just a second. And then it's either going to keep going that way, or it's going to turn around and go that way. Please don't think that they always turn around, because I'm going to go ahead and tell you on the basic problems that's going to work at the beginning, they are always going to turn around. But as you get the more advanced problems, they don't. All right, pick a number, pick a time between 1 and 3. 2. Put 2 in there. Testing 2. Going to get a positive times a negative times that positive is going to be a what? Negative velocity. negative velocity. And so it's going to be going which way? That way. So we do know that t equals 1 is where it stopped and turned around. Now, it stopped at t equals 3. And does it stop and then keep going backwards? Well, it's probably going to turn around because these are the really easy ones. But let's make sure. Put a number, a time larger than 3. 4, 600, 5, 10. But you put any time larger than 3 in there, you're going to get a positive velocity. So we're going to have a positive velocity. And I'll be honest, later on I'll probably just put V with a big plus sign by it. Or V with a big negative sign. But right now we're right out. Which means at this point, at t equals 3, it starts going to the right. Question before we move on. Because if you can't get that information, you need to be raising your hand now. The train is leaving. Anna Karenina, is that right?
Yes, sir.
Is that right? Yeah, y'all learned about her in... Yeah. You've read something about her?
Yes.
What do you know about her?
A lot. I just know about the story and she gets left at the train station.
Yeah, she throws herself under the train. Yeah, you don't wave your hand now, the train's leaving. Don't do what Anna did. Anna Karenina threw herself under the train. All right, here we go. This is a number line, right? This is units of feet, miles, or whatever. What you're going to do is you need to know how far out there she went before she did what? Turned around. How do you find out how far out there she went? You're going to take this 1 and you're going to put it in the what equation? Position. You need to know where she was at when the time equaled 1. So, we're going to do the position at 1 equals, and you put 1 in there, and you get 5, is that right? Someone tell me if I'm right. 5. Position is what? 5. So, at 1 second, and if y'all want to, we'll put some numbers on here. I don't ever do that. 0, 1, 2, 3, 4, 5, 6, 7. And it could be negative numbers, but it's not in this problem. We're going to erase our little velocity information. Get it out of the way. Average velocity, who cares? We'll talk about that in a second too. Again. All right. So at the time equals 1, she is 5 units out here. So right here. And I'm not going to draw it right on top of the line because you can't see it. Okay. This is velocity at 1. So this is t equals 1. And if you want to, you probably do need to put the t is equal to 1. The position is equal to what? 5. So what's the time actually equal to right now? 1. And what happened is it was going this way. That little bouncy ball was going to the right. And it went to the right until it got to t equals 1. And at t equals 1, what did it do? It what? Stopped. All right? Is that cool? Do you know why we put it out there at 5 instead of at 1?
Position.
Position. The 1 is a time. The position is what? 5. And that line that we're drawing over there is not a time line. It is a what? Position in space line. All right. Then the particle started doing what? Backing up. What I do when I do the particle backing up is I just go right under here. Gosh, I hate doing this when I'm on the video because I want it to look good. But here we go. It's going to turn around and it's going to start going this way. It's going to start backing up. My problem is, does it back up way back here? Or does it back up to here? Where does it back up to? What am I going to put in the position equation to find out how far it backed up? Put the 3 in there, because that's where it does what again? That's where it stops. So we're going to position at 3. Put 3 in there. Would y'all like for me to show you a way to put 3 in there without having to cube it and all that? Okay. I'll show y'all a little bit of math. Bring down the 1. Where'd the 1, negative 6, 9, and 1 come? They're the what? Coefficients. Bring down the 1. 1 times 3 is 3. Negative 3. Negative 9. Add those together. 0. Position is 1. P of 3 is equal to 1. Y'all remember doing synthetic substitution somewhere back there? And you thought, why would I ever want to do that? Well, imagine this being like t to the 5th in a really long polynomial, and you wanted to know what the value was. Synthetic substitution is very, or it's synthetic is very handy. Is that all right? And you get 1. So it backs up until it gets to 1. And the position is 1, but what's the time right there? The time is how much? T equals 3. Right there. T equals 3. Then what does it do at that 3-second mark? It turns around again, doesn't it? Everybody agree it turns around? How do I know it turns around? Because at t equals 3, the positive velocity went back to positive. Turns around. And then it just goes forever and ever. And how do I know it never turns around again? Because, why? Not another 0. Not another 0. And that grasped the motion of the little particle, the little runner, or the movement. We'll stop there. Let you look at it for a second. Now, notice, we do this as we find the information. Some people say you ought to tell them to find, they move to the right, they find the position here. I like to make this chart. I want this velocity chart. That velocity timeline helps me. I want that. All right. Happy with that? Okay. Now, everybody okay? The next thing we're going to do is we're going to talk about the acceleration of this little particle. When was the acceleration positive? When was the acceleration negative? And guess how you change from positive to negative acceleration or negative to positive acceleration? You must have an acceleration that equals to 0. So I'm going to take, and I'm going to get me an acceleration formula. Y'all don't need that anymore. See? I taught you something from Algebra 2 there. Help you out. All right, let's get us an acceleration formula up here. We're going to take this right here, this velocity. Yes, you could use the product rule on that one, but why not just use the polynomial?